Hello everyone, welcome back. So in this lecture we will understand what is step up chopper, what is step up chopper, what is step up chopper, output waveform, circuit diagram, circuit diagram, waveform, 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 output equation, etc. So we'll understand these things from this lecture. So this is the circuit diagram of a step up chopper. So by using this step up chopper we'll obtain the voltage V0, higher than the input voltage Vs. So the values of L here too, one inductor, another capacitor is there in this step up chopper. So the values of this inductor and capacitor are chosen depending upon the requirement of output voltage and current, and so we can choose the value of this inductor and capacitor based on our requirement. Okay, now when chopper is on, the inductor L is connected across the supply. This inductor L is connected across the supply, and the inductor current I raises, and the inductor stores energy during the on time. So when the inductor current increase, it stores some energy. Inductor stores some energy during the on time of chopper T on. When at the time T on, inductor will store some energy. Now when chopper is off, the inductor current I flows through the diode. D, and the load for a period T off. This inductor current flows through the diode to the load for a period of time, that is T off. The current tends to decrease, resulting in reversing the polarity of induced EMF in L. So when that current is reducing, it's reverse the polarity. Therefore the voltage across the load is given by V0 is equal to V plus L di dt, that is V0 greater than supply voltage V. So that means load voltage or output voltage is greater than from supply voltage V. Now if this capacitor is connected to the circuit, so in that case it will provide the continuous output voltage V0. And diode D prevents any current flowing from the capacitor to the source. If any current will flow from this capacitor to the source, that will prevent by this diode. So step up choppers are used in regenerative braking for DC motors. It is used in regenerative braking of DC motors. Now we'll see the expression for output voltage. Now we'll see the output waveform of this step up chopper. So this 3 graph represents the output waveform. So this is the output voltage V0, I0, and this is again I0. So this one for the continuous mode, this is for the continuous, and this is for the discontinuous. Output current for discontinuous, and this is for the continuous. So one by one we'll understand. So when that thyristor chopper is on, so in that case we are getting that output voltage. This is the output voltage. And when chopper is off, so there is no voltage. Again when the chopper is on, we are getting this output voltage. So this is the output voltage waveform. Now we'll see the current waveform. So as we know that inductor is opposing the sudden change in the current, so that's why current will increase slowly, even it will decrease when the switch will be off or chopper is off. At that time it will decrease slowly, again it will increase slowly. So like a voltage, suddenly it will not be high or suddenly it will not be zero. So it will decrease slowly. So this is the, as we can see here, this waveform is not touches to this zero line. So that's why what you can say, it's in this waveform, this current waveform, so it is in continuous. So there is no break, means it will not, in between there is no zero value. So that's why what you can say, this is a continuous output, continuous current mode. And in the second waveform, so after this it is coming to zero, again it will start from zero. So that's why this is a discontinuous current, output current. This is the circuit diagram and outputs of this step up chopper. Now we will understand the expression for output voltage. voltage. So assume that the average inductor current I during on and off time of the chopper. I is the current. I is the current during on and off time of chopper. On and off time of chopper. When the chopper is on. When chopper is on. When the chopper is on, so voltage across the inductor, that L voltage across the inductor is V, and that energy stored in the inductor, energy stored in inductor is equal to VI T on. So this, what is this? This we know that P equal to VI, and energy is defined by VI into time. So that's why that stored energy in the inductor is VI into the turn on time. That switch is on for that period, turn T on period. So that's why VI into T on. This is the energy stored in the inductor. Now where T on is the on period of chopper. So this is the on period of chopper. Now when the chopper is off. Now when chopper is off. Now chopper is off. So in this condition, energy is supplied by the inductor to load. Energy supplied by the inductor to load. So voltage across L is equal to V0 minus V. So energy supplied by the inductor is equal to energy is equal to V0 minus V into I into T off. Now this is that off, so that's why this time is T off, means this is T on and this is the T off. So this is the time T off. This is the T off. So that energy is V0 minus V into I into T off. So where T off is the off period of chopper. So if we neglect the losses in the inductor, we can write energy stored in inductor L, energy stored in L is equal to energy supplied by L, inductor L. Therefore V into I into T on is equal to, that is the energy stored is equal to energy supplied. So that is V0 minus V into I into T off. So this is the energy stored and this is the energy supplied by the inductor. So we can write from this V0 is equal to V into T on plus T off, T on plus T off by T off. So if we simplify this, we can write V0 is equal to V into T by T minus T on. So where T is the chopping period or period of switching, and T is equal to T on plus T off. So V0 is equal to V into 1 by 1 plus T on by T. So therefore we can write, so V0 is equal to V into 1 by 1 minus alpha, where alpha is equal to T on by T. So that is duty cycle. Okay, so this is the expression for output voltage. Thank you.